you. Okay, but let's continue with the next few reactions, the one that have funny names, your imine, enamine, hydrazone, and oxime. So let's just start with a general molecule in here. And then we're just going to do an acid catalyst. Now, I'm just going to show you the mechanism once, because no matter what you use, like an acid or a base, you're going to end up with the same exact product. You guys know what's the difference now in the mechanism. Acid, it makes the electrophile more electrophilic. Base makes the nucleophile more nucleophilic. So in this case, just for the rest of the reactions, I'm just going to put HCl. Okay? So keep that in mind. You can have it with bases or acids. Okay. So let's start with our imine formation. First of all, this guy, what kind of functional group is that? It's an amine. Specifically, what degree? Primary amine. Exactly. So whenever you see a primary amine as your reagent, that's how you know that you're forming the imine. So if we have an acid catalyst, what's going to be the very first step? Exactly. It's going to get that hydrogen. So now we're going to have a positive charge in our oxygen, which is making it more electrophilic. Now, okay, so now we have this, and let's bring our primary amine now, because we're ready for the reaction. Primary amine is always imine. Okay, now, what's going to attack what? What do we think? The same process that we saw with the other reactions, guys. What's going to do the attack and where?
In order to attack the positive charge.
Positive charge in the oxygen. Mickey. Not quite. So remember, what's the main portion of the actual attacks for a carbanion? Remember, we have our dipole moment, right? Which means we have a delta negative on an oxygen, delta positive on the carbon, sorry. So we're going to be attacking that carbon. It's always the attack to that carbon. Now, more specifically, remember, your nucleophile is on the arrow. That's always going to be your nucleophile for this chapter. Whatever reagent you see, nucleophile, that's it. But more specifically, the nitrogen is going to do the nucleophilic attack. Remember, that makes the new connection. So to not break the octet, I push the electrons up towards the oxygen. And now I added my primary amine over here. Change. I know that nitrogen is not that happy. It has a positive charge in it. Okay, what do we think is going to happen now? How do I make that nitrogen more stable? Best guess. Fluorine comes and gets one of the hydrogens. So that could happen, yes. But for this reaction, not quite. But we know that we have to get rid of one of those hydrogens because it has too many connections. So this one is actually going to be an intermolecular step. We're going to be transferring that hydrogen to the oxygen because that oxygen is going to be my leaving group in this case. So we do an intermolecular proton transfer, which is practically just a hydro shift in a way. It's just a hydro shift. I'm just moving that hydrogen. Okay, now I have this guy, which is going to be your tetrahedral intermediate. Okay, now at this point, now our oxygen is not quite happy, but that oxygen is going to be our leaving group. So in order to kick it out, we have to reform a double bond in here. More specifically, it's going to be those lone pairs in that nitrogen go back down to reform a double bond. And then that's how we kick out our water, okay? Okay, we got to this point. This practically looks like your imine now. Remember, it's a double bonded nitrogen connected to an R group. Now, that nitrogen is not happy again. So what's going to happen? Hydrogen, it's going to go away. And now actually the chlorine comes back at this point. So your dear chlorine takes away that hydrogen. So we can neutralize our product. And now we have this little guy. And that's it. That's how you end up forming your imine. Okay, questions on the mechanism for the imine? We're good? For your dear imine. And if you just got here, please scan the QR code. You guys know where it is. On the sheet. Okay, well, I'll just show it to you. Okay. Any other questions on imine specifically? We're good? Yeah, I'm not sure if it's imine or imine. So
Professor pronounces amine like
No.
Oh.
No, he pronounced it Imine.
really.
But then you just say data as data, hence the joke, Imine.
Yeah. Okay, let's go back to this guy. Okay, so we know how to make our imine now. Let's talk about our enamine. That was the one that was shifted around. And again, we're just gonna start with a general ketone, but this time we're gonna start with this guy. Okay, now, before we actually start with the mechanism, let's review some parts of that molecule. So these two carbons, the ones adjacent to that carbonyl area, how do we call them?
What was the question?
How do we call them, those carbons adjacent to that carbonyl?
Oh, no, they're general. Shit, they're not general.
They're terminal, yes.
Lily.
Yeah, sure, it's allelic too. Beta hydrogens,
Heavy?
no.
And the answer is?
You actually said it in one of the early sessions. It's the alpha position. This guy, it's the alpha position. Okay, we have our alpha carbon. So that means that whatever hydrogens you have in there, those guys are considered your alpha hydrogens, okay?
Relative though, to what you're
To this
saying.
reaction, yes, it's
That's
very
what I'm saying.
important.
So you could label anything alpha.
That's true too, yeah. But in general, whenever we are doing reactions with carbonyls, the ones adjacent are alpha. Yeah, it's always for the carbonyl. And then the one on the left, that's your beta, but we don't care about that one. Now we know that we have an acid, so the electrophile becomes more electrophilic. So we just add that hydrogen. And now we have a positive charge. Okay. What kind of functional group is that on the arrow?
Enamine,
What degree?
secondary.
Secondary. And that's going to be your key reagent. Your secondary amines are always forming the enamine specifically. Okay, so we know that whatever's on the arrow, that's my nucleophile. So we're going to be attacking. Whoops. We attack our carbon. That's delta positive. We take up the electron so we don't break the octet. So now I have an oxygen, well, alcohol group here. And the entire second amine is getting connected there.
Will it drop the hydrogen?
Yes, it has to drop it. But let's go step by step. Okay, so that nitrogen, positive charge. We don't like that. So to neutralize it, we're going to do the same thing that we did before. An intramolecular proton transfer. So this guy is going to go to the oxygen. Why? Because that water, that oxygen, it has to be my leaving group. So let's just do our intermolecular proton transfer. Okay. So we have that, guys. So now let's switch it up. That oxygen has a positive charge now.
So you're replacing pretty much that carbonyl with the nitrogen.
Yes, in a way. Yes. Same.
Question about the second step, where you're going from the carbonyl to the carbonyl. The carbocation, shouldn't it want to stay on the oxygen because it's more electronegative, or would it rather be a secondary allelic to a oxygen position?
It's going to be favorable that it's in something electronegative, but the whole goal is to create a molecule that's not reactive. As soon as you see charges,
That molecule, pushing the carbocation in that position, put that on.
there you go. Okay, so we have this guy. Now, what did we see in the previous reaction for the imine? After the transfer, what do we do? Exactly. So yeah, lumpers go down to make that double bond, and we kick out our water finally. So now we have this guy.
You like zoom out all over, so I think.
Yes. Actually, let me show you the previous reaction.
No, but the reaction's not done, right?
Why not?
Because there's a positive charge on the nitrogen. Yeah.
There's a positive charge. And also, how does the enamine look like?
Bigger.
Okay, I'll give you that point. Yeah, it looks bigger. Plus also, we have a double bond that's composed of pure carbons. In this case, we have a double bonded nitrogen, so we have to fix that. Now, are we done taking the photos? No? We're
No,
good?
I'm just gonna wait till the reaction's done. Take one photo.
Okay, got it. So remember how at the beginning we were talking about the alpha positions. Now, in order for this reaction to proceed, you need to have alpha hydrogen specifically. Okay, you need them. If you don't have them, this reaction is not going to be able to go through. So again, we're looking at the alpha positions, those carbons. And we have our hydrogens. Okay, now, the whole goal is to shift those pi electrons to be connected to either of those alpha carbons. Okay, now, double bonds. How do we know a double bond is more stable than another one?
This
Not
with
general.
The substituents.
So it would want to go to that one with the methyl group on,
Yeah, right, left side.
because it's more stable.
It's going to be the one on the left side, yes. Because if we, whoops, wrong one.
Doesn't want to get that.
If we put our double bond there, it's going to be way more stable than put it to the right. So again, you need alpha hydrogens, and then you choose the most stable position for the double bond. In this case, it's not really about steric hindrance, yes.
In a reaction, if you were to do this in a lab, would there be, I guess, an amount that the double bond shifts to the?
Yes, but it would be very minor.
Okay.
Okay, so we have this guy. And now, in order to form the double bond, actually, we are gonna be bringing back chlorine. This one is from the very first step with the acid. It's just the chlorine. It's going to be very similar to what you guys learned for elimination reactions back in chapter 7.
Essentially, that's a hydrogen. Or is
Mm,
it because we're breaking and forming a pi bond that it's no longer? Understand what's going on?
yes, it's basically you're just shifting around the pi electrons, kind of like resonance. Now, for the hydrogen, we know that the left side is going to be the best side to make the double bond, right? So I'm going to be abstracting that hydrogen, that alpha hydrogen. So my chlorine is going to attack it. It takes it away, and then I'm just going to move my electrons there to form that double bond. And then to not break the octet, those pi electrons have to go up to the nitrogen. And now we have this guy.
Awesome.
And there you guys go. Okay, questions on the mechanism. This is the only one that's going to look slightly different than the rest of them. Okay. Now, if we have an aldehyde instead of a ketone, that hydrogen from the aldehyde, is it going to be an alpha hydrogen? If we have an aldehyde instead of the ketone, that hydrogen, is it considered alpha?
No,
No, because
Because
on the carbon that's adjacent to the oxygen.
Exactly, yes. So remember, that hydrogen aldehyde, they're not alpha protons. So if you see an aldehyde and then the other side, it doesn't have any hydrogens available, then it's going to be no reaction. Okay.
Wait, wouldn't it just react to the carbon side?
If that carbon side, if it's full, if the octet is full with just pure connections to
Oh,
carbons,
okay.
then it's not going to work. Okay, let's talk about our dehydrazone formation. And now we can go back to a simple ketone. And let's use HCl. What was the reagent for this reaction?
Enamine.
Hydrazone was the product. Hydrazine. Diamine. Yeah, technically, yes, it would be a diamine, but more specifically, the name of the reagent is hydrazine. Okay, keep that in mind. Hydrazine, reagent, hydrazone, product. There we go. Okay, so very first step, we know, really simple, that oxygen gains that positive charge because we're connecting that hydrogen from your dear acid. And now we're going to bring back our hydrazine. Okay, now, in this case, remember, practically for all of the reactions, some sort of heteroatom was doing the first attack for the nucleophilic attack portion. Now, in this case, is it going to matter which nitrogen I use, left or right? No. Okay. What would happen if one side Did it went out?
No, that's okay.
Okay. So what would happen if in one of those nitrogens, I would have an isopropyl group? Something that's,
Propyl is a electron donating. So
yes,
It's sterically
I'm not
hindered,
aware of
so
that.
you would want the electron on the nitrogen that's least sterically hindered. to react.
exactly. Now, this is not the only possible hydrazine that you're gonna see. We have something called a phenyl hydrazine. So one of the sides is gonna have a benzene group, so that's gonna be too sterically hindered. So you're always choosing the nitrogen that's less sterically hindered overall, yes.
So for that nitrogen with a benzene that you're talking about, is it the nitrogen kind of replacing one of the carbons in a way? Of a benzene, or is it directly attached to it?
Let me draw it up.
Okay.
So this guy is just your phenyl hydrazine. Okay. Okay, now, in this case, we have a simple hydrazine, so it doesn't matter which one I choose. I'm just gonna use the one on the left. We attack our carbon, pick up the electrons. And now we have an alcohol group on one side. And we have our hydrazine connected in here.
Then it's got one of those alpha hydrogens.
The alpha hydrogens or the hydrogens and the nitrogen? Exactly. How are we gonna do that?
well,
What's the name of that step? Intramolecular proton transfer. So yeah,
Oh, I skipped a step, that's right, yeah, so it's gonna go to that, alcohol group.
exactly. Because that's my leaving group at the end. Again, this is your intramolecular proton transfer. So now you have this guy. Oops. Okay, now, what do we think is gonna happen at this point?
Leaving
Double
group leads,
bond
so you'll have
forms.
I guess in a way, carbocation that'll jump to the nitrogen.
I heard of reforming.
There.
Yes, exactly. So that nitrogen is gonna basically donate those electrons to make the pi bond. And then we have to kick out our leaving group, which is just water. Okay, now we still have a nitrogen with a positive charge. How do we neutralize it? What's gonna come back? Your chlorine comes back. So now you're gonna have your neutral hydrazone.
Oh, okay.
Okay. Questions on that mechanism?
and the HCl is a reagent used at the beginning.
It's the catalyst for the reaction. Now, we only have one more mechanism to go through, okay, which is going to be your Wittig reaction. No, you don't really have to know that mechanism in full. But I am still gonna show it either way, just in case. Now, for the next two reactions, your cyanohydrin and oxime formation, I'm just gonna show you the shortcut. And then after we're done, I'm gonna show you the full shortcuts for every single one of the reactions, okay? So let's see our dear cyanohydrin, sorry. Okay, so let's just start with a simple ketone. And then we need HCN. Now, let's start talking about the shortcuts. So the reactions in this chapter, I call them the decapitations reactions. Why? Because that's practically the shortcut. So we have our carbonyl, right? Okay, now our carbonyl, that's gonna be our little person. Now, the oxygen is the head. We're gonna decapitate it. So now we don't have a head, but we still have the legs. The legs are staying the same. Now, at this point, we're not gonna replace the head exactly. We're gonna grow two arms instead. So we have a little Frankenstein in there. So we have our little Frankenstein in there with two arms. Now, on one side, we're gonna be attaching that cyano group in the X. The other one is just gonna be an OH. That's it. Simple as that. Chop off the head, grow two arms, that's it. You form your little Frankenstein in there.
Frankenstein's monster.
More than that for Halloween, huh?
Actually, yeah, right on time for Halloween. Okay, ready for the oxime? Let me start drawing this guy in here. And actually, before I show you the shortcut, we have that specific reagent. Do we know the name for that one? That's the oxime formation, yes.
I'm gonna guess hydrazone.
Pretty good guess, actually. The actual name is going to be hydroxylamine. So this guy is just your dear
I tried, man.
hydroxylamine.
That's
Okay, now, same process. Chop off the head. The legs stay the same. Now, in the previous reaction, we created two arms. That was our Frankenstein. This time, we're going to switch it up. It's going to be the head. We're going to switch up the head specifically. So in here, I still have my double bond. I'm just going to replace that oxygen for my nitrogen in here. I connect my nitrogen, and then the only remaining portion of the reagent is going to be the nitrogen with the alcohol group. The hydrogens, we're not connecting them, because if we do, then we're going to get a positive charge in there. Simple as that. Questions?
and it pretty much kind of mirrors the other reaction,
Yes, exactly.
like where we drew it all out.
Mm-hmm. We had a question. No, we're good. Okay, we have enough time to show you the reaction in here. Do I? Okay, yeah. Okay, let's continue with the mechanisms and then the shortcuts. So last reaction, the one that most students hate, is your Wittig reaction. So the Wittig. Yes. Let's start with the general reactions. So again, all of the reactions that you're seeing here can be with either aldehydes or ketones. In this case, I'm just gonna label my R groups. Actually, no, let me change this. R3 and R4. And then I'm gonna have, whoops, not an oxygen. Okay, no. That guy with phosphorus. How do we think it's called?
You said it's Phenyl with the phosphophenols hydrazone.
So probably one of you guys is correct. That should be like the full IUPAC name, but we're just gonna call this reagent the elite. It's just gonna be the
boy.
elite.
Where did he come up with that?
So yeah, there was no way that you guys were gonna guess this one. So more specifically, this is your inactive elite.
They said randomize it. We're gonna do a count.
Okay, now this is the inactive elite. The active elite is gonna have some partial charges, but for the shortcut, we're gonna keep it in the inactive form. Now, same process as before. Chop off the heads, this time of both the actual molecule and the reagent. And now our Frankenstein is gonna look slightly different. We're gonna be combining the legs together, okay? We don't have heads anymore, we just have pure legs. So I'm gonna keep the legs from my ketone, R3 and R4. I'm gonna have now a double bond and then connected to the other side. Now I'm gonna have R1 and R2.
What about the ENZ? Like, how does that go? Like,
You always wanna form the trans one, but in this case, because they're just generalized, it doesn't really matter. And then technically your byproduct, before you guys ask, is gonna be this guy.
would you make ENZ? Oh, I see.
There we go. Okay. Questions so far? We're good?
That's a O and a phosphorus, 3 phenyl.
Yes. It's basically the head of the heads combined together. So yeah. One Frankenstein just has pure legs, the other one has pure heads. That's it. Okay, now. That's the shortcut, but now we have to start talking about the actual mechanism. How to make your dear elite and the actual full mechanism for this reaction. Because you might get a question on the transition step. So just in case, let's show it. I know you guys don't want to learn it, but still, you have to. Okay. This guy is going to be your triphenyl phosphine. Okay. And let me show you the hydrogen specifically here. Okay, so to make your elite, you need a triphenyl phosphine. So that's just like that phosphorus connected to the other phenyl groups. And then you need an alkyl halide. Remember, the X, it just represents any sort of halogen you want. So in this case, our dear phosphorus is going to be attacking our carbon with a halogen. And then remember, halogens, they're good leaving groups, so we're going to be kicking it out. Now, at this point, you're forming this guy. And actually, let me move it. Okay. Now, for the creation of your elite, you need some sort of base. Okay, it can be any sort of base. Usually the one that he likes to provide is going to be, whoops, that's not correct. Basically a benzene group with lithium. Now, this guy is just a base. It can be any sort of base, but usually the most common one that you're going to see is that guy. So our dear base is actually gonna, different color, and attack our hydrogen. So then those electrons are gonna be moving to that carbon. So now we're gonna have a neutral product in a way, because positive and negative, they're gonna be canceling each other.
Phosphorus.
Yes, but that's not the goal. We want to have that charge separation.
Can you go back to the previous step just a little bit? Active leaving group. What's that part up? What do we call that reagent? The CH, is that an Li?
Yeah, it's a benzene group with lithium.
Okay.
So we have R1, R2. And now that we have that even charge separation, we have positive and negative, they cancel each other, neutral. That guy is your active ylide. In this case, let's just write active ylide.
So then that molecule stays with that positive and negative.
Yes. And we're actually gonna see how that plays out for the actual mechanism. So let's start with the same ones. Okay, now, again, we're starting with ketone or aldehyde, doesn't matter. And now we have the active ylide. So this portion is gonna look similar to what we saw during diazoxide. So specifically, we know that as soon as we see a negative charge, this guy is gonna be your nucleophile. Plus remember, for this chapter, ketones, aldehydes, they're always the electrophile. Now, that carbon specifically attacks our carbonyl region. We have to kick up the electrons towards the oxygen so we don't break the octet. And then we're gonna attack back the ylide, specifically that phosphorus group. So this was your first arrow, second, and third. So now we have our little intermediate. So it's gonna look a little funny. Okay. I know it's a lot. So this is your intermediate and it looks basically like a square. Okay, that's usually the one that he likes to test on if he does give you any questions on the mechanism at all.
Question.
Yes,
I'm so confused about like how do we know that R1 and R2 will stay in their place and not flip?
we're technically both versions are going to be created.
Okay.
In this case, it's just to generalize the actual mechanism. And now, just in case the name for this guy is going to be quite long. Oxaphosphatate intermediate. So yeah, I have no idea how to pronounce that, but you guys get it.
Oxaphosphate thing, that's
Thank you.
not too bad.
Yeah, but still,
There's like E leads and E means that's pretty bad.
I like the elites.
You know the E leader.
Okay, so now at this point, we're going to be creating both forms. Okay, so we have R3.
Wouldn't it be
Or-
like 4 forms of this then? Or this like the R3 and 4 switch and then R1 and 2 can switch?
I mean, yeah, you're correct on that one.
Right.
But usually he just likes to focus on 2. Yeah, he doesn't really show the 4 possible ones. R2, R2, R1. So at this point, that's how you form both E and C isomers.
That's actually.
Okay. Questions on the mechanism? Yeah, it's interesting, quite a lot. Oh, sorry, I didn't show you the byproduct. So this guy is basically just floating around as your byproduct. pH3 plus, there we go. That's your little byproduct.
Yeah.
Like those things combined to treat the oxide.
Are you talking about the end product? That's where it says E and C.
Question, I don't think you flipped it. That's not easy.
Oh my God, I
Same
didn't flip
side.
it, right? Yeah,
Okay.
that's on me.
Just keep one the same.
Great catch. Thank you, guys. Okay, ready for the shortcuts now. For all of the reactions. And I don't think I included it in the handout, so you guys are gonna have to take a picture of the spider web.
You said what? We have to take a picture.
Yeah, probably. I didn't include it in this handout.
I'm just gonna use that. for
No, the spider web that I'm about to show you for the shortcuts.
Oh, you said you didn't put this.
Well-
Okay.
Yeah, no, because I wanted to
So
go through
this
the
will be
mechanisms
on-
first.
Yeah.
We're gonna skip that portion. You guys should know that at this point. Now, this one. Let me zoom out actually.
The
We don't want-
contrast is horrible, I'm sorry.
But
Is that in the handout?
it's not in the handout, so start taking pictures. You're gonna get this once the answer key is posted, but start taking pictures. Now, it's a cute little spider web that's summarizing the entire chapter, basically.
Wanna send me that picture?
Absolutely.
Wait, make sure you can see the contrast. You can barely see the yellow.
best it's gonna be.
To be completely honest with you.
Can we turn off the lights, actually? Ah, stay there. There we go.
That one, oh, that's so weird.
Oh, that's crazy.
Okay, let's just keep it like that for now.
Hey, yeah, here, you got, send me that. You don't. No, send me that.
Are you good? Are you good?
Wow, this is so bright. I hate that.
You want it?
Yeah, what's that?
Yeah.
What's
Okay, everyone's done with the pictures?
I got it.
Okay,
I don't remember like live.
I'm missing one more.
I got 2 weeks, so you can keep the lights off. Good seeing you. My- no, it's- Good runs.
Okay, so let's start from the center and right. Okay, we're gonna move like a clock in here. So remember, you can start with any ketones or any aldehydes. If you see any other carbonyl groups, these reactions are not gonna happen. Okay, that's the main portion. Now, this portion, we have our alpha hydrogens. That's highlighted just because of one reaction, your dear enamine formation. Now, let's start with our gem diol formation in this case. So practically, this is gonna be like the memorization portion. As long as you memorize the spider web, you should be good for the exam. Okay. So remember, decapitations chapter, we're always chopping off the head of the ketone or aldehyde. Now, in our product, in our reagent, we always get rid of some hydrogens because if we add the entire reagent, then we're gonna have like a positive charge somewhere. So in this case, chop off the head, grow 2 arms. In those 2 arms, we just have our alcohol groups that came from the reagent. Simple as that. Now, next one, we have an alcohol group. Remember that carbon chain is very important. Whatever you see there is going to get connected at the very end. But we get 2 different products with acids or bases. So again, same process. Chop off the head, and for all of the products, you're creating arms. Okay? You're just adding some arms. Now, if you start with the acid, that's when you create the full forms. That's why you have your ketyl or acetyl. If you use a base or no catalyst, actually, you just end up with the hemiforms. So hemiacetyl, hemiketyl, those guys. Okay, so it's not too bad. It's practically just chopping off the heads, growing 2 arms. That's it.
I can see that.
So in this case, we see what kind of functional group is this?
Hydrazone.
Amine.
Amine, what degree?
Primary.
Primary. So we know that. That's my amine formation. So again, chop off the head of the carbonyl. Chop off the hydrogens from your reagent, and then just switch the heads. So instead of oxygen, now we have nitrogen here. That's it. Now, degree.
Then
What's the name of the reagent?
secondary amine.
Secondary amine. Beautiful. Now,
Yeah.
Mhm.
Essentially, you want the carbon.
So chop off the head, move the double bonds.
Okay.
so yeah, here's the thing. Quick disclaimer. Shortcuts are not for every single student. Some students prefer to see the full mechanism. So do whatever works best for you. Okay, so this portion, same process. Chop off the head. And now, instead of growing the full head, like with a double bond, we just have one single bond, and we're going to be connected to that reagent, okay, to that nitrogen. And remember, this is the only reaction where you're shifting around that double bond. So you're always choosing the most stable side. So remember, this guy is more substituted. So overall, we're just going to choose the left side to create the major product. And that's it. And there are your rules. So you need alpha hydrogens, and then hydrogens from your aldehyde, they don't count. Okay. Then your hydrazine, this guy, same process, chop off the head, chop off 2 hydrogens from the less directly hindered nitrogen in there, and just swap the heads. That's it. And then last 2, your oxime formation again, chop off the head, chop off the hydrogens from the reagent, swap the heads. And then for your cyanohydrin formation, we're not creating a head, we're creating arms. So one arm is going to have my cyano group, and the other one has my alcohol group. And that's it. So practically, you're always chopping off some sort of head, and you're creating either a new head or arms.
No, but this pretty much summarizes it. This is the entire chapter, right?
Yes,
Like this one page is.
this one page is
That's
the
great.
entire chapter.
That's like the most concise summary.
So yes, I love to do these things for any chapters in any classes. Appreciate it. Okay, questions?
Not this specific picture.
It's going to be posted in the answer key. So just wait for the answer key.
So wait, is this the end of 15 then, if this is the summary?
End of 16, yes, but we have to do practice problems, which should be pretty easy now that we know the shortcuts. Okay, so we're going to do those Monday. We have 2 pages. And then this portion, I'm just going to fill it out because you guys know this. It's practically the same thing that we did before each of the reactions, labeling, and that's it. Just for your sake, I'm going to complete it. And then we just have to talk about reactivities, and that's it. We're pretty much done with 16. For sure, yes, but maybe 18, depending on how fast your professor goes through the chapters.
Yeah.
A lot of questions.
Diagram real quick.
Spiderweb?
Yeah.
So you want me to turn off the lights again?
What's, is 18 easy? What's 18?
Oh, it's not the easiest chapter.
She said, oh, wow. We
It's all about tautomers.
polymers.
So
I have a question, so just kind of a statistic
Yeah.
thing. So this class average for this test, exam 2, it
Mhm.
was higher than expected.
it was expected. We
So-
expected an increase in average from exam 1 to exam 2.
Right, between the two.
He-
Right, but what about,
Yeah,
you know, a previous semester ago, let's say, exam 2, did he include chapter 15? He
it
didn't.
always varies semester by semester because it
Okay.
depends on how fast he goes through the exams. But usually they have the main key chapters. Exam 1 is always going to have chapter 9. Exam 2 is always going to have chapter 13. So that can give you like a baseline, but yeah, the average is like pretty similar to what we've seen past semesters. Pretty much the same thing. Chapter 17 is about reactions with carbonyl groups that are not ketones and aldehydes, which is actually really fun. Okay, and we have shortcuts, so don't worry about it.
I definitely got the one. I was looking at sugar cane one. Super sitting right next to that. And I just see four conjugation problems. And my exam, that's reaction. Almost like.
Oh, it's like something. Yes. But there's no exam code. I'm thinking it's like, question 2 could be different questions, but it's gonna be.
Oh, I understand what
That's
you're saying.
my.
I have a question when you're done.
Yes,
I just figured it out.
it's okay, I can go there. I'm just trying to check if we have the full average now.
You have?
No.
You know what happens.
Go ahead.
Yeah, exactly.
Do you think?
Okay, no. Okay, makeup grades are not posted yet. Yes.
I need a coffee, bro. Fuck it up.
Alright, so I have a question, right? Which one was this? Oh yeah, I think it was. So like this one specifically too, right? Like Cardigan's two. So I know that BR2 that was like that could be ortho or
The product is not D,
not D.
it's C.
Oh yeah, I had picked C.
Oh, okay, you're good.
Yeah, okay. Well, because that's I mean that'll be the less therapy hindered one anyway. right?
Exactly, that's why it's their major.
Okay,
But did he ask for the major product or all
I
possible
think
products?
this one was.
Consider the reaction below to answer the following questions. This product D is,
Okay,
can
yeah,
be
so
either or.
Yeah, I can do either or.
so it can be B or C.
There was a specific one I was, I think it was this one right here, okay.
Don't sweat the
So
small stuff.
equal, I know for a fact, I was saying 3 is the least therapy hindered one. But the only option of 3 is 1, but 1 is like super therapy hindered since it's between both the.
Yes.
But would 3 not be the best one, like?
3 is gonna be the best one because we have overall like lesser hindrance in that molecule, so it's pretty much stable. Now, number 1, technically, it is gonna be created, but it's a theoretical product because it's so clustered,
Yeah.
we don't wanna create it. But in this case, it's just for the sake of the conceptual stuff. So it's gonna be equal to the amounts of 1 and 3.
Okay, and then there was this one right here, I know this is right because this is like, this is the electron withdrawing and then
Yeah.
this is electron donating.
Exactly.
So you would want it the
On the right.
this one.
Mhm.
Okay, but I think let me see, question 1, is it? Yeah, this one was like
1.
This one's 1?
1.
How? Wait, let me read. Okay, yeah, bromobenzene and para. Is it because the chlorine is on just the para position?
I mean, they're all in the pair position, if you see. It's all about the carbocation. Technically,
okay.
positive charges or any charges at all are better with electronegative atoms. But in this case, he was asking, I think, for the intermediate or major
It's
one.
definitely between 1 and 2,
Yeah,
right?
it's.
Yes,
So I
but
think the
specifically
difference
it's
is the
one.
sense of the positive charge and
Yeah.
and it's next to the double bond right there.
Yeah, that
See the double
too.
bonded bromine?
Yeah, I see
It's
that.
vanillic, but in number
Oh, yeah,
1,
yeah,
it's
It
allylic.
would much rather be
Oh,
on a
oh,
tertiary
yeah.
than on a
Oh yeah, I
vanillic
forgot. Yeah, the
position.
carbocation, yeah, the vanilla and hollow.
Yeah.
Mhm.
And then question 2, the positive. So this one right here, you would just. I remember honestly I can't remember. This one you just have to determine which one's like the deactivator, and activator,
Final
and which one's
cumulative,
stronger, right?
Yes.
Yeah, it is.
Cumulative.
So I know NO2 would stay in this position, and I was saying that wouldn't it be the chlorine?
So
How come
what,
it's the chlorine that doesn't attach in this way? CH3 instead?
what kind of reaction are you doing in there? Is it
Oh,
halogenation?
this is between like acylation or alkylation, right?
Mhm.
So since it's not like a ethyl group, since it's just like one bond, wouldn't this just be the alkylation?
Acylation, remember, we have some sort of carbon group in there.
Okay, so this would be alkylation.
Alkylation, exactly. So we chop off our leaving group, fluorine goes away, and then whatever carbon chain you're
Oh
removing,
yeah, I guess it's attached on.
you get attached. But NO2, what's that? Activator or deactivator?
NO2 was it was like more down the list. So that
Strong
was-
or
yeah,
weak?
It was a strong one.
Strong one. Alkylation, that's the only one that has special rules.
Oh yeah, because the Friedel. Okay, yeah. So what's the whole thing about the Friedel's reaction again?
So Friedel cross reactions, they're not gonna happen whenever you have any strong deactivator.
Oh yeah, so it's just not gonna
So,
react at all.
exactly, it's not gonna react
No,
at
it
all.
is. I thought it was NH2 that doesn't react. It's
NH2,
and
it's
O2.
also as well.
Oh,
Any
also-
amines or any strong deactivators.
Okay. So if it was NH2 or an O2, they both don't react.
Exactly.
Okay, so this would just be which one doesn't react?
combination.
Let me just do three, since it's not, oh, wait, no, that's not three.
No,
Oh,
it's
my
just
bad.
gonna be no reaction.
Oh, and I didn't.
He gave you the option, yeah, don't worry.
Okay, alright, that makes sense.
Okay, good,
I appreciate it.
no problem.